Alright friends, welcome back. In this video I'd like to go ahead and continue our discussion of section 3.4 from your textbook and just expand on a little bit of what we talked about in the previous video. So as always, if you haven't had a chance to get that one watched, then please do that before continuing on with this one. In this video specifically, I just want to go ahead and take a look at a couple of additional examples that you might be up against here in this section and show you how to do them, right? So in order to do that, we're going to need the help of a new theorem here. So basically it's phrased as an if-then, and basically this has to do with whenever I give you zeros that are actually complex numbers, okay? So numbers that look like a plus bi, all right? And so if you take a look at what the theorem says here, it's a simple if-then. It says if a plus bi is a complex zero of the polynomial function f of x, right? So if I were to give you the fact that one of your zeros is a complex number, then automatically its conjugate, we say, is also a zero, okay? So again, what is a conjugate? Well, we talked about this back when we first talked about complex numbers, so those videos are still live, so if you want to go back and watch them, you can feel free to do so. But a conjugate of a complex number is basically the same complex number, but instead of the addition sign, we put a minus sign, and vice versa, okay? And so it's super easy to find the conjugate. The numbers a and b will stay the same, and of course I, that is the imaginary unit, that's the square root of -1. Again, the conjugate is just the same exact complex number, but it uses the inverse operation, okay? And so what this theorem says is that if I were to ever give you a list of all the zeros of a polynomial, if one of them is complex, then we are automatically going to throw its conjugate into that list as well of all the zeros. Okay, so where that comes up is down here in this first example, where it just says write a polynomial function of least degree that has real coefficients, the given zeros, and a leading coefficient of 1. Okay, and so these zeros here are numbers that, again, if we were to feed them into our function machine, it would output 0. That's why we call them zeros of functions. And you'll see here that I did give you one of these zeros is a complex number here, and so I gave you 3i, all right? Now that may not look like the a plus bi form that we were talking about earlier, but if we rewrite it, then we can find here that is actually the exact form that we want, because we could just go ahead and rewrite this as simply 0 plus 3i. And that will do the trick, okay? Then we can more easily match it up and see that playing the role of a is 0, playing the role of b is 3, okay? Well, if that's the case, then according to our new theorem, we have a fourth zero in this list, and that is just going to simply be the conjugate of this complex number that we were given. And so if that already reads 0 plus 3i, the complex conjugate would read 0 minus 3i. Remember, the only thing that changes, of course, is just simply the operation in the middle. Okay, so that would simply reduce down to negative 3i, and so that would be the fourth zero in our list of all the zeros here. Okay, so that's just something that you have to keep in mind from now on. If I ever give you a list of zeros and one of them is a complex zero, you're always going to have to say that its conjugate also belongs in that list. Okay, and so our goal here up in the directions is we want to go ahead and write a polynomial function, and that polynomial function has to have these 4 zeros. Okay, so I'll recall your attention back to something that we talked about in the previous video, which was that for each of these zeros, they each correspond to an algebraic factor in the factored form of our function, okay? And so just in general, just so we make sure that we have this written down somewhere, in general, if I give you a 0, one of those inputs that makes the output 0, right? If I give you a 0, maybe let's give that a name, let's call that a, then in every case, that's automatically going to translate over to a factor in your factored form. And that factor is going to look like x minus that number a. Okay, so we're going to have an algebraic factor that looks like that if we have a 0 that looks like, say, the number a. So for each one of these zeros down here in this list, we are going to make an algebraic factor that goes with each of those zeros. So starting at the top of our list with the number 0 itself, we would have an algebraic factor that looks like x minus 0. And I know that x minus 0 is just simply x, but just for purposes of being able to match this up to the pattern, we'll write it like that for now, okay? And then for the next one, 5, we have x minus 5. For the next one, that's our first complex 0. That would be x minus 3i. And then you got to do a little bit of thinking about that last one, right? That's a negative 3i. So we could write that as x minus negative 3i. But remember that minus a negative, that would just simply change the operation. So I'm not going to write it as minus negative. I'm going to change that to plus 3i. Okay? And so again, for each one of these zeros, I can write down an algebraic factor that goes along with it. All right? And so now that we're here, we're going to use these algebraic factors to figure out what our actual function formula is going to be. And the way that we're going to do that is just simply by expanding some things out, okay? And so since I have 4 factors here, I'm just going to go ahead and do these in pairs, right? So let me go ahead and multiply the first 2 together and figure out what that's going to be equal to, right? So we'll say that this is equal to, now, of course, the x minus 0, that's just simply x, so I'll write it down as such. So x times x minus 5, and then if we were to use distributive property and distribute that in, that would simply equal x squared minus 5x, okay? And so that, of course, is what we get there by doing that first initial green part, which I'll go ahead and lump up in a set of parentheses just to distinguish it from the other thing that I'll do, which is the last 2 binomials there, which I'll go ahead and do in blue here, okay? Now, that is multiplying 2 complex numbers. We had a whole video talking about operations with complex numbers in the past, and one of the things that we talked about is that anytime you multiply a complex number times its conjugate, it's always going to be a difference of 2 squares, okay? So if it's been a while since you've seen the difference of 2 squares, if you have a product that looks like u minus v times u plus v, we might remember that this is always going to be equal to whatever u is squared minus whatever v is squared, okay? So that was back when we first talked about factoring, and then again when we talked about complex numbers. So you may want to go back and watch those videos if you forgot, okay? So again, you could FOIL this out if you wanted to, but that would be more work than just applying this simple formula here. So now that I know that it applies, I'm just going to go ahead and apply it, okay? So I'm going to say that this is going to be u squared, and playing the role of u is x, so I'll say x squared, minus v squared. And playing the role of v is going to be that imaginary number 3i, which I'll go ahead and write as squared here, okay? And so this is my blue part so far, and to figure out the rest, we just need to go ahead and figure out what 3i squared is, okay? Now, that is something that you could do in the calculator. Again, check your complex number videos in order to figure that out, but here I think we could just do this with some mental math, right? Because 3 squared is 9, and I squared by definition is -1, and so because I'm squaring 3i, I would just need to multiply 9 times -1, and that would give me -9. So I could, again, write this as x squared minus -9, but that double negative there, that would change the operation, of course, to a plus. So I'm going to write that down as a plus 9, and then that would be the result of multiplying those 2 complex numbers together. So again, you would get that same result if you went ahead and just FOILed out those 2 complex numbers, but here I think that goes a little bit quicker, okay? And so now that we have this simplified down to just a binomial times a binomial, it would be at this point that we would just want to go ahead and continue by using our FOIL method, okay? So first, outer, inner, last. And again, we've done some videos in the past about explaining FOIL methods, so I'm not going to go through that too deeply here. I'll just point out that your f in FOIL is going to be x to the 4th. Your outer is going to be plus 9x squared. Your inner is going to be -5x to the 3rd. And then your last is going to be minus 45x, okay? And that looks an awful lot like a polynomial function to me, but one of the problems with this is that it's not in standard form, and that's something that we always need to work towards if it's not in standard form already. So we're going to rewrite this so that the exponents descend. So I'm going to write my first term as x to the 4th, and then minus 5x to the 3rd would be the one that comes next, and then follow that up with a plus 9x squared, and then finally your minus 45x, and that would be your function formula for f of x, okay? So this is going to be our answer to the problem right here, so I'll box that. And really quickly, I just want to go ahead and make sure that this matches the description from up here in the directions. So first of all, it said to write a polynomial function. I definitely think we ended up with that, right? So this has a sequence that looks like a number in front of x, and then the x with some exponent on each term. So that's a polynomial, definitely. And then it says it has least degree. And so one of the things I want to call your attention to is from the last video, we talked about the fundamental theorem of algebra, which a corollary to that, or a direct consequence of that, said that you're only going to have as many zeros as the degree of your function. Okay, so our degree of this function, of course, is 4. And we had 4 zeros that we started with, so that makes sense, okay? Does it have real coefficients? Well, I believe yes. All the numbers in front of x are real numbers. There's no I in my final answer, so that checks out. Does it have the given zeros? Well, we used those zeros to get this function formula, so I think we're safe to assume that, yes, it does have those zeros. And then finally, does the leading coefficient look like positive 1? Okay? Well, yes, the number in front of our x to the 4th term is a positive 1 there, so that checks out as well, and so we know we have the correct answer here. Okay? So again, just kind of summarizing that process, for each one of those zeros, you get an algebraic factor, and then it's just a matter of expanding out those factors to get your final function formula there, and then just doing the brief check to make sure that it passes all the tests of your directions here. Now, part B, you'll notice that I left blank, and I'm going to continue to leave this blank. It turns out that part B has a significant amount of challenge to it, which I would go ahead and offer that to you. If you want a challenge here, it would be the exact same steps as what we just took a look at, but because your complex number is given to you as a binomial, it will present some more challenge than what we just previously saw here for part A. So if you think you're up to the challenge, then go ahead and give that one a shot, and feel free to always check that with me if you're interested in what the right answer would be. These next couple of examples here in example 2 just go along with what we talked about in the previous video, so I'm not going to go ahead and discuss them here, but I will go ahead and just leave them on the screen for a moment, and feel free to pause and check my work here and see that we have a couple of examples where in part A it looks like you have both a real 0 and then 2 complex zeros, whereas in part B it looks like you just have simply 3 real zeros. So again, if you're looking for the process by which you would take to solve these types of problems, go ahead and check out your 3.4 day 1 video, but I'm going to skip them here. The last thing I want to go ahead and talk about here in this video is going to be this question right here. So it says, example 3, given a 0 of the polynomial f, use long division to find all of the zeros of f. So I'm just going to do part A here, and then we'll call it a video, okay? So you notice here we're already given the function f of x. It's just simply equal to x to the 4th power minus 81. And then I gave you a 0 of this polynomial, right? So negative 3i is going to be a 0 of this polynomial. That can be what you plug in to make the output 0, all right? Well, in order to solve the problem here, one of the first things we'll point out is our complex conjugate root theorem, which says that if I gave you one of your zeros is a complex number, then its conjugate is automatically also a 0 of your polynomial here. So we'll go ahead and point that out, that the conjugate of negative 3i will be also a 0 of this, and so that will just simply be the opposite sign, which is just simply, of course, positive 3i there. Okay, and so now that we're looking at this, we remember what we talked about in the previous example, which was that each one of these zeros corresponds to a factor in the factored form. And so let's just go ahead and write those out here, right? So we can go ahead and write out some factors here, and those factors would simply just look like x plus 3i and then x minus 3i. Okay, and it turns out that that's the exact same product that we took care of in the last example, so I'm not going to show the steps again. You could either do FOIL method or look at that as a difference of 2 squares, but however you expand that out, you're going to be ending up with x squared plus 9, okay? And so what this means is that this is going to be a factor of our original polynomial. You might say that x squared plus 9 goes into x to the 4th minus 81, okay? But that kind of begs the question, you know, it would be this factor, but then times something else. And the goal of the question is to figure out what is that something else, okay? And so in order for us to figure that out, we need to go into the directions and see that they recommended that we use long division here. And that actually is going to work out really well, because if x squared plus 9 does go into x to the 4th minus 81, then we should find that after long division, there should be a remainder of 0, okay? And so let's go ahead and set that up for ourselves here, right? So our divisor is going to be x squared plus 9. Keep in mind, we do need some placeholders for terms that we're missing, so I'm just going to introduce my x term by saying plus 0x there, and then we'll just simply say plus 9. That's our divisor. That goes outside the long division symbol, and then inside the long division symbol, we're going to put our original function with some placeholders for terms that we're missing in the standard form sequence here. So I'll say plus 0x to the 3rd plus 0x squared plus 0x, and then pick up with the constant that I was originally given, which was your minus 81. And then we'll set up the rest of the long division in that way, okay? Now, I'm not going to go over too deeply how we perform this long division here because we did that in a previous video, so I'm just going to go ahead and blaze through that process here. We're going to have an x squared to start. That's going to result in x to the 4th plus 0x to the 3rd plus 9x squared, and then we subtract, okay? And so we're going to find here that your x to the 4th column cancels, your x to the 3rd column cancels, and we're just going to be left here with 0 minus 9, which is negative 9x squared. And then we're going to drop down the next 2 terms, actually, because what we're trying to do in this line is match up to how many terms are out here on our divisor, which we can see with that placeholder is 3 terms. So we're going to drop down the 0x, and we're going to drop down the minus 81. Okay, and so now comparing, we are going to see here that a minus 9 will do the trick, so we'll distribute that into our divisor and write the result below here. So that'll be negative 9x squared minus 0x minus 81. and then of course doing the subtraction here, we are going to see that not only does your x squared column cancel, not only does your x column cancel, but also your constants cancel here too. That's negative 81 minus negative 81, and that would become 0. And so we have nothing else to drop down, so that must mean that this number that we ended up with here is the remainder, which is 0, which we said makes sense, because if we did want the x squared plus 9 to go into x to the 4th minus 81, we said the remainder had to be 0 after the long division, okay? And so what we can conclude from this is the following, right? Our original function was given to us as x to the 4th minus 81. Okay, what we just figured out according to those complex zeros is that one of the factors of this polynomial is x squared plus 9, and then after doing the long division, we found that the other factor was x squared minus 9. That was the quotient after doing the long division. Okay, and so we were able to take our x to the 4th minus 81 and factor it in this way. And since we're tasked with finding all of the zeros here, we would just need to go ahead and pick up from here in our factoring and then find all the rest of the zeros. Okay, and so we'll go ahead and say here that this is going to be x squared plus 9, and then x squared minus 9. Again, this is just one of your special factoring formulas. You might recognize that as a difference of two squares. We can always factor that in terms of x plus 3, x minus 3. And then to find all of your zeros, of course, we're just going to set each one of these individually equal to 0 and solve. And we already know what kind of zeros we're going to get out of that first factor, because that was just the two complex zeros that we were originally given. So I'll just say that here, negative 3i and then positive 3i. But then as you set these other two factors equal to 0 and solve, we're going to see that we get some real number zeros here. So the first one will give us x is equal to negative 3, and the other will give us x is equal to positive 3. In which case, if you take a step back and look at how many we ended up with, this is 4 separate zeros. We have 2 real zeros and then 2 complex zeros. And that makes sense, because if you remember the fundamental theorem of algebra from the previous video, it said that the number of zeros is going to be the degree, okay? Or at least at most the degree, okay? And so we have 4 zeros here. We had a polynomial that had a degree of 4, so that checks out, and that will complete the problem for us here, okay? So again, the point of this video is to point out that anytime you have a complex zero, its conjugate is also automatically a 0. And also, if you have a 0, it always corresponds to a factor that looks like x minus that number. And then you can expand those factors out to get your actual function formula, okay? So that's all I have for this video here. Feel free to let me know if you guys have any questions over any of this stuff. I'm always happy to answer whatever questions you have, but thank you very much for your attention, and I will speak to you in the next one.